Hello and good morning, good afternoon, good evening, and thanks for joining to today's Neo4j Live. Hello, Philip. How's it going? Can you hear us?
Hey,
Yes. Hi.
yes, for sure.
Cool. You're joining us from Colombia today, so South America. So if the internet connection is not holding up as it did in the test run, then we might have to switch on a plan B, which is turning off the cameras. But for now, I think it looks quite well. But if anything goes wrong, please excuse it. It's due to maybe internet connectivity issues. Um, yeah. Thank you for joining. It's another Neo4j live session today. I'm hoping this will be fun. I'm very much looking forward to it because recommendations in general is a great topic that comes up very often. Usually, we hear it regularly. It's a good discussion point. It's a good use case of graphs, a good use case of Neo4j, obviously. But now today we're combining it with the GDS machine learning pipeline. So it's kind of like one step up because we talked about recommendations for quite a while, but with in combination with GDS, I think we haven't talked about it so much. So I'm personally also looking forward to today's session. Before we dive in, I'd like to quickly talk about Nodes, which is our online developer conference in November. 16th and 17th of November. Currently, the call for papers is still open. Here it says closes at 20th of August, but we extended it for a couple more days. So if you are interested in speaking at Nodes, if you have a topic that is interesting and you'd like to present there, go to the website and submit submit to the call for paper. Otherwise, obviously you can already register now. So if you think it's gonna be cool, and I'm pretty sure it will be good, then you can go there and register already for the event in November. Yeah, that's what I wanted to share here. But now let's dive into the topic. Before we do that, Philip, maybe you want to share a few words about yourself, who you are, what you do, um, and how do you how did you come across Neo4j? How what you know what is what does graphs play? What role does graph play in your life, basically? Yeah.
Yeah, welcome everybody. I'm from Colombia. I'm actually in Medellin at the moment. My name is Philip, and I'm a freelance software developer, like big data engineer from Munich, and I've had quite some contact. I've been working the last 2 years mostly with graph databases and machine learning. And yeah, from time to time, I also create some blog posts or videos about topics I can come across. It's basically like this one. And today we're going to talk about building a recommendation engine with the Neo4j GDS pipeline. And it just happened that I came across or studied a little bit the GDS pipelines, and I wanted to share my learnings from having a look. And the focus of this talk will be more theoretical. So we're going to talk about these steps that are required to set up what each of the steps does. And then there are some hints that one should take into account, but we are focusing on understanding what are the principles based on. So yeah, I think that's my introduction. So if you want to follow me, you're gonna find my name.
I put it
yeah.
in chat, so your blog and your Twitter. So yeah, definitely follow Philip. It's very interesting what he does.
Thanks. So, shall we get started, or is there more?
I think we can get started. Yeah, I mean, I just while you get set up or while you click on the share screen button, I wanted to say we try to keep this usually interactive. So if you have any questions, anything you'd like to know, and maybe we can make a short detour here and there depending on what the questions are. We are happy to see what what you have in mind, and what I mean, if you used your recommendations before, if you are using yourself Neo4j for recommendations, maybe you can share some learnings as well. Yeah, I'm excited. I'm looking forward to this, and yeah, we can always pause for a bit of a short discussion at any time, I think.
Yeah, exactly. Please go ahead and shoot any questions right in the moment as they appear. I'm just gonna share my entire screen. Can you see this presentation now?
Yes. Let me get this out of the
Wonderful.
way. Here we go. Yes, perfect.
Great. So as I mentioned before, it's going to be a theoretical talk about the GDS pipeline. So I studied it a little bit, and so what came to me making this video this session is basically a video I recorded about building a recommendation engine based on a naive Bayesian classifier, which is a very simple approach, which basically leads very promising results as well. But the drawback of that is, I don't know if anyone has watched it, but you're basically modeling the approach directly into a Cypher query. And like the advantage is that we can shoot this query in real time against the database, so we don't have any overhead for deploying different systems. But the disadvantage is that as we want to consider one feature as it is at the moment, it's going to be very complex to model, or it's becoming more complex as the more feature we add to this query in the end. So I came to look into this link prediction pipeline, which is a slightly different use case though. But it basically combines some of the things, because we can have easily more features while we still don't need another technology, like for example, a Python framework or a TensorFlow setup or something like that. So we don't need external resources, but we can run it within Neo4j, even though it's quite resource intense to train these models, I guess. So there might be probably a different infrastructure for before we can give recommendations on our price. And what I want to do here is walk through how we can design such a pipeline. So the traditional machine learning pipeline consists of basically 3 steps. So there's feature engineering, which is probably the most important part and where we put in the most work. So we need to extract features and select the right features, where we also need tools to do that, and we iterate over this process. And usually we have directly associated features. So in this case, there would not be node features, but for example, a row in our table would be one set of features for one data point. And we can also more features, for example, like a word embedding or something like that. And then we got to select the right features, which we then in turn feed into our model training and evaluation. And here we basically have to select the right model and parameter space. Then we have to do the tuning of the parameters, and we're going to select the right metrics so that we are measuring, so that we can measure the ability of our in the end, before we can use the model to give predictions. And with graph machine learning, it's actually not so different, but in particular, a link prediction pipeline, we need one additional step. But on the feature engineering part, we are in the graph database, we have basically more options. So we don't only have the directly associated node features and the inferred features, but we can also have graph features, which basically are metrics, like graph metrics about the connectedness of a node. So for example, number of neighbors and so on. Or we could even apply graph algorithms to infer new data, for example, like node embeddings or centrality detection or something like that. And the feature selection is still the same. So it's even more complicated or more complex because we have more options to choose from. And in this prediction pipeline, we have an additional step here in between, because we are usually dealing with a pair of nodes rather than one node, doesn't directly apply to the most of the well-known machine learning algorithms. So that's why we need this step in between. Here we have basically the same steps. So we got to select the model, the parameters, and the metrics. And we can give predictions in the end. So what I would like to start with is the general source graph. For the prediction, for this use case, we are talking about a homogeneous graph, which means that we have only one single type of nodes, so one node label. And we have relationships between them, which are all the same. So, for example, we have here users who know users, and the relationships are considered undirected, like depicted here. So users, and there's no, so that it's always a bidirectional relationship. And that's a very special grant. So, but for now, we're going to be talking about this. So the problem we are trying to solve is we want to predict a link. So, for example, so we can consider a recommendation for a source user. We can recommend others which he might know. So we're trying to predict links which are not yet in the data or missing in the data. And that's what we're going to do. So we're going to predict future or missing edges. And we can also state this as a binary classification problem, where we basically take a pair of nodes, in this case, node 1 and node 2, and we want to predict a class, and the class, there are basically two classes, which is class 1, which is we want to predict a link, and class 0, which mean that there shouldn't be a link. And that's a basic problem statement in this case. The second part, which is very particular to link prediction, okay, let me go one step back because it's on the slide here. So here the two nodes, they have features. One set of features would be node features, which are the directly associated features like age, location, interest, or properties of a user. And then we have graph structured features, which we can derive from the graph structure. So there will be a triangle count or an out degree connectedness of the node. And we could apply graph algorithms, which try to analyze the entire structure of the graph. And therefore, we assign new features to each of the nodes, which basically measure their role inside the graph. For example, like graph embeddings, page rank, centrality detection, similar to what I said before. And now to our link vector generation, as I talked before. Now, as we don't want to predict a label for a single node, but rather we want to predict a label for a pair of nodes, basically here node 1 and node 2. We want to know if they are connected or not. So we have a pair of nodes rather than a single node, and therefore we got to combine their feature vectors. So x and 1 is the feature vector of n1, and x and 2 is the feature vector of n2. And so we have two vectors in this case, but we have to combine them into one vector in order to be able to feed them into our machine learning model, which only takes one vector, of course. And this is called the link feature vector in this case. And for this combining function, we have multiple options. In the graph GDS library, at the moment, there are 3 implementations of such a combiner. The first is the L2, which is basically the squared distance. So it's the difference of the two vectors, and the distances are squared. So basically, it's the distance, and it yields a vector. So the combination of vector xn1 and xn2 become a vector. Then we have the Hadamard distance or product, and it's basically only the element-wise product, so it's just a product of the vectors. And we have basically a cosine similarity, which is something similar to the angle between the two vectors. And only the last one here yields only a scalar. So if we combined these two vectors with the cosine similarity, we would get back a single number. And one important thing to notice is that the GDS offers to combine different features with different such combiner functions. So for example, if we had one feature in the 3 vectors, the first 3, so that could be a node embedding with 3 dimensions. And the second one has also a node embedding with 3 dimensions. So we could combine them with a different like combiner function than, for example, the second feature. And in the end, the combined vectors would be appended into one large vector of X. That's just a side note about the implementations. Are there any questions until now, or should I just continue?
Oh, I think I don't see any questions. Again, open invitation. If you have any question, anything you want to know in chat, please just type it in. Yeah, no, I think we can go ahead.
Please feel free to interrupt me because I don't see the chat window also. All right, so that we so that's the part about feature selection and the combination into a link vector. So once we have done these steps, one additional thing to keep in mind is the balancing and splitting of the input data that we want to put into our model. Because in this binary classification model, we have basically a very imbalanced data set. If we look, for example, this small example graph, which I made up quite randomly. So what we need is basically positive examples and negative examples to train our model. And a positive example is, for example, is a existing relationship in the graph. So node 1 and node 6 would be a positive example for having an edge. So an example for class 1, and node 1 and node 3 are a positive example because there is existing an edge in our graph. So that we use to infer the decision function about how we can say that there should be an edge. On the other hand, we need negative examples, which are basically all non-existing relationships in the graph. And these act as examples for our class 0, so the prediction that there shouldn't be an edge. And usually these graphs are rather sparse, like with most recommendation engines. Because if we look at that graph here, we have in total 10 nodes and 14 edges. But each node, like the node N1, could have 9 edges in total and has 2 positive examples. So there must be 7 negative examples for this particular node. So if we extend this to the entire graph, we can calculate how many edges there could potentially exist between all of the nodes, which is n times n minus 1 divided by 2, which would be all the edges possible, minus the edges that are existing, which are 14. So there are 31 negative examples in our graph, but only 14 positives. And if we were to train our model based on this data without filtering or without pre-processing it, we would end up with a model which would very likely predict class 4, which would mean there shouldn't be an edge, and it would have quite a high accuracy because it would be right most of the times. Therefore, we gotta give it some thought how we should sample these negative examples, and it's basically called negative sampling. But the splitting occurs on the positive samples. So the splitting into test and train sets happens with examples. So what I try to depict here is that circle stands for all the positive examples in our graphs. And here we can see that these are basically all the edges between the nodes. Now we split these positive samples into a positive test set, positive samples, test set of positive samples, and take around, like the default configuration in the GDS is 10% positive samples we have in the graph. And the remaining samples are called the samples complement set. So these are all the edges without the edges in the test set. And it's not the training set, but rather it's the positive complement set And that's a word which basically, like this set comprises basically the train set and a feature input set. So the positive complement set we in turn split up into the training set, which is about 10% by default, and the remaining of it is the positive feature input. So the positive feature input set is basically a subset of the positive samples, a quite large one, which we don't use, like these examples, we don't use in training or testing. We only use them for the calculation of the features. For example, a graph embedding or a page rank, or all these algorithms, which can occur in the features and extraction step. Do filter out the test and train sets so that we simulate that the algorithm didn't know the edges because we want to predict them. So we simulate that the two predict edges wouldn't exist as they do if we basically apply or want to give predictions in the end. There we wouldn't know if the edges existed as well. So it's a way to measure if our features actually work without the edges in it. Okay, now we've split our positive samples into 3 sets, and now we need to sample also negative samples for each of them. So this circle depicts all the negative samples we could potentially have in our graph, so all the non-existing edges. And we sample them to the same size. It's also configurable how large the negative test set should be compared to the positive set. But let's assume that we sample the same size. So that's what I depict here with this pie piece. And we also sample a negative test set, which is the same size as the test set. Oh, it's a negative train set, actually. It's wrong here because the test set is here and here's the train set. So we also sample the train set to the same size as positive samples. And one thing to note about the sampling is that there are many approaches to do negative sampling. At the moment, GDS supports only random sampling, but I think it's in research topic itself. So these are just some examples I found for negative sampling. So nearest neighbor sampling, for example, uses a graph embedding approach to find samples like negative samples which are similar to the positive samples. And there are many approaches and they work differently on different data sets. So that's something where you can do a lot of research in your model and improve it, also like in the feature part. But I'm not an expert on this. I haven't researched all of them in detail, but I just know there are many, and if you have problems with your model, you could look at sampling strategy in the end. But to have balanced data sets, for example, test set or train set, that's a very important thing to keep in mind. So that's it about sampling input data to model. Now we would use this sampled or input data to basically train a binary classification problem, which is where we have two sets in the GDS at the moment. There are 2 implementations, which is a random forest or a logistic regression. And that's the formula of the logistic regression. And we would basically put our input data, which consists of the nodes and the labels we found in the graph, or like the positive samples have the label 1 and the negative samples have the label 0. We would put them into the optimization function, and what it basically does is way beyond the scope of the session, but we would score them to probabilities, our equation here with the softmax function, and the cross entropy loss function here would basically compare 2 probability distributions. So it's the difference between 2 probability distributions, and the one distribution is basically the prediction of the model. That's this formula, and it compares the prediction of the model against the labeled probability distribution, because the which we can consider as a probability distribution as well. So we are minimizing difference between the two, and therefore we optimize our problem here. So the result would be a vector which contains two probabilities, one for each class. So the first column here, or the first element in the vector, is the class 0, and the second element in the vector is for class 1. So ideally, for a positive example, the second element would be larger, and for a negative sample, the first element would be larger. Now, the GDS link prediction pipeline, it also offers you to add multiple models to your pipeline. So you could, for example, even add both, like a random forest and a logistic regression. And you can also specify spaces for the parameters. And it offers a cross-fold validation, which would figure out what's the best model and the best parameter instance for you. And therefore, it would split the training test sets again into basically the train sets into k-folds. Exactly. So that's the only things I think we gotta know for the model step. And in the end, to measure the predictions during the training, we also need to specify the metrics we want to use for evaluating the skill of the model. So how good is our model in the end? Now, as I said before, the result of our model prediction would be that for each pair of nodes, we have the label, which is the input or the target. And we get back a prediction, which is a probability distribution in the end. And we can, for a binary classifier, we also have a threshold for which we consider a probability as part of a class. So for example, if we had threshold 0.5, so once a probability is above 0.5, we would say, okay, it belongs to that class. So in this case, the second element is 0.8, and it's greater than 0.5. So we say label is 1, so we get a true positive. Or if we classify it wrong, we get a false negative in this case, because we would classify it as negative, but actually it's positive, so it's a false negative, and so on. And there are 4 classes of errors we make, which is true positive, false negative, and true negative. And these we can use to optimize our threshold that we set. Because let me talk about precision for a moment. Precision is a measure which basically gives the positive, which is basically the ratio of true positive predictions, so the actual which are correctly positive, divided by all positive predictions we get. So it's the rate of positive predictions we make, the ratio. And the recall in turn is the ratio of true positives we have over all positive examples we have in the graph. Because we divide here, there's missing the brackets, I'm sorry for that. Because that's the denominator here, the entire thing actually here as well. So here in the denominator we have correct positives plus the incorrect positives, which like the positives in the graph which we classify wrong. So the denominator is basically the sum of all positive examples we have in the graph, and we see how many we predict correctly about them. So if we look at these, we set different thresholds for classifying our predictions. We could actually steer the trade between false positives and false negatives. And to make this a little bit more clear, I want to have this one. So if the prediction is going down, that means the denominator is going up, and as the true positives is the same everywhere, the false positives have to go up. So if the precision is going down, we have more false positives. So we are more aggressive towards labeling something positive. We are rather labeling something positive than negative. And if the recall is going down, we have more false negatives because the denominator is getting larger here. It's more towards a passive true prediction. So here we say, okay, let's be a little bit more conservative about saying something is true. So the thresholds are actually higher. Missing. Yeah, here's the plot. So I've taken this from a website that I read this. It's very useful to read this, I guess. So if we set different thresholds, we get different values for the precision and recall. So this is, we go over all the thresholds that we could set, and we get a graph about how the precision and recall behave against each other. So this plot basically plots the recall on the x-axis and the precision on the y-axis. And we can basically infer for which threshold we get which precision and which recall. And we can see if the recall is going up and the precision is going down. So this is an entire plot. But to optimize our model, we basically would take the area below this curve to get an average, which is basically an average over all the thresholds, to say how good our model, how well our model performs in general. And that would act as a single metric for one model, which is basically independent, or which is summed over all of the thresholds that we could put set. And this we use in turn to find the best model. So here I have an overview about what happens to the data once we execute this pipeline. First, we take the positive feature input and we sample also the negative. Here we don't, sorry, here we actually don't need negative samples because we use the set to calculate node props based on graph algorithms. So we would just apply our graph algorithms here with all the nodes present, but some edges are filtered out because we want to predict them. So here we calculate the nodes in the first step. And then we take the positive train set. We sample negative training samples. So we have an equal and balanced set for training. We calculate the link vectors for each of the pairs we have as examples. And then we split this into k-folds. So we split it into subsets of these two sets. And then we train and evaluate multiple models, which we in the end compare against each other and select the winning model. And this winning model we use together with the train set. So we train this winning model on the entire train set and then evaluate it with the entire test set. And this is the final model that we have, and that we can store in the GDS also in a model catalog. And this catalog we can use to make predictions. While making predictions, we also need these steps here on the to predict nodes. But in the end, we use this model to make predictions with the GDS pipeline. And that's basically the end. What I wanted to say is it's a general overview about what we can do, what the steps are. The fun part basically occurs in the feature engineering step, where we can calculate new features, extract new features, and then we evaluate models, and we gotta measure the ability of the model to see how well it performs, and then we basically iterate over these two steps with our pipeline to basically optimize our model. So there we have a lot of possibilities. Also, the GDS allows for many features that can be extracted from graph data. And potentially in a future session, we can have a look at some of the examples, how we could do that on a test set, for example. Now, as this is the end of the session, of my part of the session, I wanted to ask if there are some questions, and yeah, let me know if there's something else that you want to know. Yeah, I'm happy to hear your feedback.
Cool. Thank you very much, Philip. Yeah, if you have questions, please put them in chat. Uh, this was a lot of information, I think, in a short time. So very condensed, very interesting, and very specialized. I guess if you watch this and don't have so much background knowledge on machine learning and on graph data science, maybe this was a bit too involved. If it was, don't worry. Obviously, this will be a recording, will be online, so you can watch it later. Um, we have further material also, so to go into the graph data science in general. If if I think about it, is very interesting. The process you showed when you say you take a test and then you do a positive sample, you do a negative sample, and then you run tests against each other to see what the results would be like, and then um, the, where would you see is a good point of making a decision? I mean, now you would basically get um, the precision goes up, and the and where would you find, okay, this is the point I need to say, this is the cutoff point here. Basically I say, okay, now from here on I go, I basically I have I use the data, I look at it, and this is the point where I say, okay, now it's either this or that. um, is there a best practice, or would you say this is, because this is, I guess, the tricky bit, then, to say, okay, now I have my positives, I have my negatives, but then when do I decide, is this a link, yes or no?
Yeah, yeah, that's an interesting question, and that's basically what it comes down to if we develop such pipelines in the end, because it's highly dependent on the use case. So for different use cases, you would make different choices. For example, there might be use cases where you really want to avoid false positives. There's one famous example which would be fraud detection, where it's very costly to chase down one positive classification.
Mm-hmm.
So here you don't you want to have less false positives, whereas in other use cases you might not care so much if there's one or two false positives more. So you would rather go for less false negatives. Yeah.
Yeah.
So it's highly dependent on the use case, but what you would do is use these graphs to evaluate your model and look at it on a visual basis as well,
Mm-hmm.
to also see how different features improve or not improve your model. It's a way of measuring how well it works, and basically we iterate over this process many times to find the right setup for the pipeline.
Yeah, that's a good point. Yeah, but Ramdas says demo would have been helpful. Maybe we do a demo as a follow up. So at a later point in time, this was now yeah, we just couldn't do a demo this time around. But this is a good base, and either we do it together at some point, or Philip posts a blog post sometimes, maybe, and then we can link this video to the demo part for sure. So yeah, to see. Question from Cam: would development be done in Cypher, or are you calling from a Python notebook or something else as a subroutine? I mean, yeah.
That depends
Yeah.
actually. Like, you can define these pipelines in Cypher. So these are just GDS statements. So you have a Cypher script which you want to run, but you can run them any way you like. So you can run them from Python or from some notebook, whatever your setup is there.
Yeah. So yeah, I think that's a preference. What you prefer. Um, the um, the graph data science. If you are, I think what we always say is, if you are well versed with Cypher, it's probably a little bit quicker to do it directly inside Cypher. Although now with the latest release on Graph Data Science, we have a dedicated Python driver. So I think the parity is almost there. So it's more like a preference, what you prefer, how you work, what you feel more comfortable with. Use the either or the other, and then you know yeah. Cool. I don't see any more questions. Any I don't know, any final words from you, Philip? Anything you'd like to share on this topic?
Yeah, maybe one thing only actually. So the GDS, they're making a large effort to basically enable machine learning directly in Neo4j. So the traditional use case, how most people, and that's what I see in projects as well, is that we execute some graph algorithms in the database, and then we export everything into a Python or Pandas or whatever, and use machine learning libraries there. And then we write them back to a graph database or whatever. And they're making a huge effort actually to enable this entire process to happen within just a single framework. And when I did the research, I was actually surprised how many things are there already. So you could, if you're working with things like that, you can definitely check them out. Also, the documentation is very well. So if you, because we haven't looked at the syntax and how to do it in the end, but the documentation has examples for everything. So it's a really great thing to look at. And yeah, thanks for joining here today. It was a pleasure for me, and hope you all have a great evening now.
Thank you, Philip. I just posted the link to the Graph Data Science landing page at neo4j.com, where you find the general overview, what it is, what it does, and then obviously in our docs overview there is also here it is, the current manual for the Graph Data Science library. Let me also add that into the chat here. So we have so you have that, and I think, yeah, like I said, it's a very intensive library now. It's constantly getting updated. So since I think this year already, a couple of iterations have been pushed out, and we are currently at version 2.1. And every time it's improvements, more algorithms, better performance, and all of that. So it's it's a good tool. Try it out if you haven't done so. You need to use Neo4j Sandbox if you want to give it a shot. So that's cool. Yeah, and maybe we'll be back later at some point and doing this as an actual demo to showcase how it can be done, and then go about the topics you just said about writing actual code, and see how that would look like, at least in a demo environment. Until then, yeah, totally. Thank you very much, Philip, for presenting, for showcasing this. This is very interesting, very thought-provoking, to quote Mark on chat. So I think people liked it a lot. Very interesting topic. Thank you for taking the time. Thank you all for watching. We'll be back on Monday, Michael and I, with another Neo4j Aura stream. So tune in on Monday if you like. Until then, yeah, I wish you all a great week, and yeah, see you soon. Take care. Bye.
Thank you.